with a geometric sequence. A geometric sequence can be used to describe the growth of bacteria in an experiment. On the first day of the experiment, there were 9 bacteria in a petri dish. On the 10th day, there are 3 in exponent 20 bacteria in the dish. How many bacteria were in the dish on the 7th day of the experiment? So first of all here, let's use the explicit formula for the geometric sequence. And we already know, just let me write here the formula so we don't have to look back anywhere. So A sub n is equal with A sub 1 times R, the common ratio in exponent n minus 1. So this is. And here, in the first day, there were 9 bacteria. A1, A sub 1 represents the first term. In the first day, how many bacteria were in the dish, in the petri dish, to be more specific. But because here we are dealing with the 3 in the 20 and 9 we can write as a 3 in exponent 2. So I want to use it this way because I know I have to work with the 3's something, because I have 3 in the 20. So now R, we don't know the R, we don't know the common ratio because it is not given and we don't have enough elements to determine what is R. So now A in the 10, A sub 10, so in the 10th day, let's write it just in a general form, is A1, A sub 1 times R, if n is a 10 here, 10 minus 1 is a 9. So R is in exponent 9. So now, instead of the given here, A10 and A1, let us substitute with the given values. So A10 is a 3 in exponent 20. So let me write here, 3 in exponent 20. On the other hand, A1, we already have here, is a 3 square. So it's a 3 square. The first term is 3 square. And we have here R in exponent 9. So now we can simplify a little bit of this equation. So because here we have R squared, we wanted to divide both sides by R squared, 3 squared, I'm sorry, 3 squared. And when we divide both sides by the 3 squared, in this side remained just R in exponent 9. But in the other side, on the left side, 3 in exponent 20 divided by 3 squared is going to remain 3 in exponent 18. So that's what we have here. And now we are using the properties of the logs. Properties of the logs in both sides. The properties of equality of the logs. And we have here a log of 3 in exponent 18 is equal with the log R in exponent 9. So now here, what we have here now, with exponent R in exponent n. With the R in exponent n, let me write this like a log. Now we are using these properties of the logs, the power property of the logs, and 9 gets in here in the front of the log, and 18 gets in the front here of the log. And we have 18 times a log, common log of 3 in exponent 18, common log of 3, because 18 already is here. And in the other side, we have 9 times a common log of R, common log of R. And on both sides, we divide by 9, because in the left side, I want to get rid of the 9. And 18 divided by 9 is just 2. 2 log of common log of 3 is equal with log R. And now again here I am using the properties, the power properties. This square I can put again in a 3 here, and we're gonna have a log in 3 square is equal with the log, common log of R. But now again we are using here the the equivalent property of the logs, here is R, just let me write R to not forget. And when we are using those properties, equal properties of the logs, equality of properties of the log, then 3 squared is going to be equal with R. And we already, just let me write a different color here. So R is equal with 3 square. 3 square. So we already got to the R. But what do we need here now to find? We need here to find the a in exponent 7. I'm sorry, the 7th term, a sub 7, which is equal with the a1, and is R in exponent 6, one less than the index here. So now we have enough elements because a1 is 3 squared and the common ratio is 3 squared. So, and a1, just let me write in here so I don't have to look back, is equal with the 3 squared. And now the 7th term, a in the 7th, is going to be equal, now whatever I have a1, we are going to substitute with the 3 squared. And now instead of the R, we are substituting 3 squared. So it happens to be both numbers the same common ratio and the first term the same 3 squares. And here is an exponent 6. And now a in a 7, a sub 7 is equal with 3 squared time. And now 6 times 2 is 12 times 3 in exponent 12. And by applying the exponents properties, that's what we are doing in this cases here, and in this case, in this case, in those two cases, in those two equations. So now we are writing the same base 3, and we add in the exponents, which is 3 in exponent 14. So we can live in this way, or if we wanted to be, for example, more creative, and we want to, not more creative, but we want to be more specific, we can find this value 3 in a 14 in a calculator, which gives us a perfect number, and is 478269. So this number here is 478. When you calculate, is 478. And let me see it one more time. 2969. 2969. So this many bacteria are going to be in the petri dish in the 7th day. Just let me, 4,782,969 bacteria.